Hello students, in this video we continue with chi-square applications, and the second application of chi-square is for the case when we are given two qualitative attributes and we are looking for any sort of association or dependence between the two qualitative attributes that we call chi-square as a test of independence. So test of independence using chi-square. Now the questions or the exercise is this one, which is quite relevant as far as students, their approach and their future life is concerned, their career is concerned. That's an important question. So tell 12.25, the US Bureau of Labor Statistics gathers data on occupations of employed workers by sex and publishes its findings in Employment and Earnings. A random sample of 83 employed workers yields the following data. So data for male and female we are provided, and four different occupational categories are given in the data set. That's managerial and professional, technical, sales, administrative, service, and other. And we are asked for testing the hypothesis as, do the data provide sufficient evidence to conclude that there is an association between the characteristic gender and occupation type for the employed workers? Use alpha equals 0.01. So let's start writing down the null and alternative hypothesis. First, we prefer to write alternative hypothesis because that reflects the statement that we are asked to test. And the testing statement is, there is an association between the characteristic gender and occupation type. There is a significant association, rather we can write it down preferably as, there is a significant association between gender and occupation type. This OT is representing. There is not a significant association between gender and occupation type. Now, level of significance we are given as no point no 0.01. Test statistic has a formula same as the one we have used in chi-square goodness of fit test. That's same F naught minus FE whole square divided by FE inside the summation sign on the entire fraction. Now critical region, same as chi-square goodness of fit test, this test is also a right tail test always. No point no 0.01 chi-square, no point no 0.01 for the degrees of freedom. We need to consider both the factors that we are given in rows and in columns, and since we are applying the concept of statistical independence, So we need to multiply these two together. R minus 1 times C minus 1 gives us the DF. Here, the number of rows are 4. 4 take away 1 times the number of columns are 2. 2 minus 1 would give us 3 times 1 as 3. So DF is 3 and significance is no point, no 1. So 3DF and significance is 0.01 gives us 11.345 as the critical value. 11.345. H naught would be rejected if chi-square calculated exceeds 11.345. Now we go for computation, and in computation we need to draw the entire table in this way. We have OT or occupation types here, gender male and female here, and the total of each row we can tally here. Whereas the first is managerial and professional, second is technical sales administrative, third is service, and fourth is others. Now, what we do, we can subdivide each cell diagonally into two parts. And above the diagonal, we will write down F naught values, what we are given in the data, and the computed FE values we'll write down beneath the diagonal. So 14, 10, 24. Then we have 9, 16, 25. Then we have 4, 6, 10. And 4 and 20 and 4, 24. The grand total is 83. And the column totals are 47 and 36. Now, how do we compute each cell value for its associated FE? For this, we need to apply the concept of matrices. The very first cell has the address first row, first column, and we can write it down as A11. Now, according to the cell address, we need to consider the total of corresponding row and the total of corresponding column. Multiply these two together because we are applying the concept of statistical independence, and then divide it by the grand total. Like this, first row total is 24 multiplied by first column total is 47 divided by 83 is the grand total. And this is how we get 13.59. That's 13.59 6, or we can simply write down it as 14 because these are the number of individuals. So 13.59 is 13.6 and 13.6 can be rounded off to 14, and then that would be 10, and we can work this out as A12, first row and second column, 24 times 36 divided by 83. So 24 times 36 divided by 83 gives us 10.4, and 10.4 can be rounded off to 10 because these numbers are representing individuals, and individuals cannot be measured in decimal places. So for the next one, that's A21, the row total is 25, the column total is 47, again divided by 83 would give us 25 times 47 divided by 83 gives us 14.15, that we can round off as 14. A22, that's 25 again, which is the same row total, but the column total changes to 36 divided by 83. So 25 times 36 divided by 83 gives us 10.84, and 10.84 can be rounded off to 11. So that's 14 and 11, and the total is same as 25. Now for A31, the computation is the row total is 10, the column total is 47 divided by 83. So that's 470 divided by 83 gives us 5.66, and 5.66 can be rounded up to 6. Then A32, 10 times 36 divided by 83 is 4.34. That can be considered as 4. So that's 6, and this is 4. And now for the last row, the expected values can be computed as the fourth row total multiplied by the first column total divided by 83. So 24 times 47 divided by 83 gives us 13.59. That's 14. And then A42, 24 times 36 divided by 83. That's 10.40 or 10.41, that can be rounded off to 10. So this is 14 and this is 10, gives us 24. I can tell you a shortcut way of computations. Whenever we have only two columns involved in our computation, we need to compute only the first cell expected value, and then we take away from 24 or the row total this computed value that would give us 10. Same answer. Similarly, if we have computed this as 14, 25 take away 14 would give us 11 as the computed value. So this is how we can do it in a shortcut way. Now, what we need to do? we need to in fact copy down on the next page the entire table, and now moving to the next page, we'll continue our computations, copying each f naught value with each or corresponding fe values as 14 with 14, 10 with 10. I'm copying it row wise. Then we have 9 with 14, 16 with 11, 4 with 6, 6 with 4, 20 with 14, and 4 with 10. And now we need to take the difference, raise it to square, and divide it by Fe so that we can compute chi-square value. And that's 14 take away 14 is 0. This is also 0. 9 take away 14. Take this difference raised to square. That gives us 25. And 25 divided by corresponding Fe value would give us 1.785. So 1.79 we can round it off. 16 take away 11, that's 5. Squared is 25 again, but this time we need to divide it by 11 as the corresponding Fe value. So 2.72 is the computed value. Now 4 take away 6 is 2. 2 squared is 4. 4 divided by 6 is 1/3 or 2/3 and no point 67. This is again, this one is 2 square is 4. 4 divided by 4 is 1. This gives us 1. Then 20 take away 14. This is 6. Squared is 36. 36 divided by 14 would give us 2.57. And then 4 take away 10 gives us 6. 6 squared is 36. 36 divided by 10 is 3.6. So we add them all. 3.6 plus 2.57 plus no point 0.67 plus 2.72 plus 1.79 plus 0 is nothing. So the sum is 11.35. Now comparing it with the chi-square value we obtained from the table, that was 11.345. So 11.345 and 11.35 are very closer. But this is crossing the borderline, which is for the rejection region we have drawn. So H naught is rejected, we can say. So decision is, since chi-square chi-square calculated value or calculated value of chi-square falls in the rejection region, therefore H naught is rejected. And conclusion we can write down as, since chi-square calculated falls in the rejection region, therefore H naught is rejected, and the test results are statistically significant at the 0.01 significance level, and data provide sufficient evidence to conclude that just mention the statement given in the Olive hypothesis that there is a significant association between gender and occupation type. So that's all for this topic.